So in this session, we will continue to look at solutions to CSEC Advanced past paper questions, and we'll be looking at a question from 2021. This is from section 4 and number 6, which deals with probability and statistics. All right, so let's jump into the question. The question says, part A, number 6, two fair tetrahedral dice with faces numbered 1, 2, 3, and 4 are rolled. The numbers obtained on the turned-down face of each die are noted. Create a sample space table listing all possible outcomes for the two dice. So let's proceed to establishing that. So we have two dice. So one die, two dice. So let's see how many rows are we going to need here. One. Let's see now. Another one there. 2, 3. Right. So let me see now. All right, so let's proceed. Let's see. Which other thing here? Right. All right, so this is what our sample space table is going to look like. For the top part, we're going to call that die 1. So this is D1. And for the bottom part, let's call it D2. And both dice are tetrahedral with numbers 1, 2, 3, 4. Right, so let's put in those possibilities. For die 2, we have 1, 2, 3, 4. Right? And for die 1, we also have 1, 2, 3, 4. So the possible combinations, of course, are 1, 1, 1, 2, 1, 3, 1, 4. Similarly, here we have 2, 1, 2, 2, 2, 3, 2, 4. Continuing, we have 3, 1, 3, 2, 3, 3, 3, 4. And lastly, we have 4, 1, 4, 2, 4, 3, 4, 4. So basically, the first number in this combination represents the number that is turned down face of die 2, and of course the second number represents the number turned down face on the turned down face of die 1. All right. So that is our sample space listing all the possible outcomes for the two dice, right? Now let's see what they ask us to do now. All right, so first part B of the question says, using your sample space table created in A or otherwise determine the probability of obtaining a 4 on both dice. Now let's try to reason it out. Now the probability of obtaining a 4, how do I represent that now? Let's say a 4 on die 1, and that's going to be U intersect a 4 on die 2 is equal to the number of outcomes where we have a 4 on die 1 and a 4 on die 2. Right? That's just a better way of representing it. Now, if we go to our table, how many outcomes do we have? A 4 on die 1 and a 4 on die 2. The answer there is 1, which is this right here. So we have one outcome where we have a a 4 on both dice. And so the probability of obtaining a 4 on both dice is equal to the number of outcomes of obtaining a 4 on the 2 dice divided by the total number of outcomes in the sample space. And if you count the number of outcomes in the sample space, essentially we have 4 across by 4 down, so that gives us 16. So we have 16 possible outcomes in the sample space, and therefore the probability of obtaining 2 4s or 4s on both dice would be equal to, 1 over 16. So this gives us 1 over 16, right? That is for 1 mark. Good. Now, the next part of the question says, calculate the probability of obtaining a 4 on at least 1 dice. So the key expression there is on at least 1 dice. So what does this mean? The probability of obtaining a 4, so P of 4 on at least 1 die, not 1 dice, but 1 die, is equal to the number of outcomes where we have at least, so that is greater than or equal to 1 4. How do I put this? A 4, right? Let me rephrase this. So the number of outcomes where we have at least 1 4. So let's write it like that. So the number of outcomes where we have greater than or equal to 1 4 divided by the total number of possible outcomes in the sample space. So I'll repeat. The probability of getting a 4 on at least 1 dice is equal to the number of outcomes where we have a 4 on at least 1 dice divided by the number of possible outcomes. And by the number of 4 on at least 1 dice, that means number of 4s on 1 dice or the number of 4s on, on both dice. So 1 die, both dice. So if we go to our sample space and we look at the possible events or outcomes where we have at least a 4 on at least 1 dice, meaning a 4 on 1 dice or both a 4 on 1 die or both dice. And let's go and check those, right? So here we have a 4 on 1, a 4 on 1, a 4 on 1. Here we have a 4 on 1, a 4 on 1, a 4 on 1, and finally we have a 4 on both dice. So when you count up all of that, how many outcomes? 1, 2, 3, 4, 5, 6, 7. And so therefore the probability of obtaining a 4 on at least 1 dice, right? That should be on at least 1 die, but anyways, on at least 1 die would be equal to 7 over 16, right? Good. So the probability of obtaining a 4 on at least 1 die, because die is a singular, dice is plural, right, is 7 over 16, all right? Now, part 3. Now, part 3 wants us to determine the probability of obtaining a 4 on exactly 1 die, right? So once again, the word die is refers to 1, but dice refer to, the word dice refers to more than 1. So we want to calculate the probability of obtaining a 4 on exactly 1 die. So if we do this, we go back to our sample space table and we look at the number of outcomes where we get a 4 on exactly 1 die. And those events are already circled. Here we have 1, 2, 3, 4, 5, 6. And so therefore this gives us 6 over 16, which can be simplified to give 3 over 8. So therefore, the probability of getting a 4 on exactly 1 die is equal to the number of outcomes with a 4 on exactly 1 die divided by the total number of possible outcomes, which of course gives us 6 over 16, which we express in its simplest form as 3 over 8. All right? So the answer there is 3 over 8. Now continuing, the part 4 of the question says, show that obtaining a 4 on both dice are independent events. So once again, we're supposed to show that obtaining a 4 on both dice are independent events. Now, what exactly do we mean by independent events? Now, let's say, for instance, we have two events, A and B, and these events are independent. So if A and B are independent events, it means that the probability of A and B occurring together is equal to the probability of A occurring on its own times the probability of B occurring on its own. So this is the requirement for events to be independent. Now, if we go back a little bit, we will see that from part B, we found the probability of obtaining 4s on both dice. So we can say that the probability of obtaining a 4 on die 1 and a 4 on die 2, of course, is equal to 1 over 16, right? 1 over 16. Now, to show that these two events are independent, we must now work out the probability of obtaining a 4 on die 1, right? And this is going to be equal to the number of events where we have a 4 on die 1 divided by the total number of possible events, number of events in the sample space. So if we go back to our table, in how many events do we have a 4 on die 1? So die 1 refers to those going across. So we have 1, 2, 3, 4. And so this gives us 4 over 16, which of course simplifies to give a quarter, right? Similarly, since we want to find the probability of obtaining a 4 on die 2, that is equal to the number of outcomes where we have a 4 on die 2 divided by the total number of possible outcomes in the sample space. And once again, if we go back to our table, we will count the number of outcomes where we have a 4 on die 1, die 2 rather. And we're talking about going vertically downwards, so we're going to be 1, 2, 3, 4. So we have 4 events where we obtain a 4 on die 2, and of course 16 total possible outcomes. And so therefore this gives us 4 divided by 16, which also give a quarter. Now let's check if these two events are independent. We say that the probability of obtaining a 4 on die 1 times probability of obtaining a 4 on die 2 is equal to 1 over 4 times 1 over 4, which gives us 1 over 16. And since the probability of obtaining a 4 on die 1 and a 4 on die 2 is equal to 1 over 16, then this tells us that these events are independent, right? So therefore, obtaining a 4 on both dice are independent events as verified by our calculation, right? Now, let's look at part 5. We'll just make some space. Now, let's see, we might need something here. Part 5 says, determine the probability of obtaining a 4 on both dice given that a 4 was obtained on at least one dice. So let's try to word this a little differently. So our in obtaining let's try to express this using probability. So we say that the probability of obtaining, say, a 4 on both dice. So we're talking about a 4 on die 1 and a 4 on die 2, given that a 4 was obtained on, how do I express this now? On at least one die, right? So this is basically expressed this. So the probability of obtaining a 4 on both dice, given that a 4 was obtained on at least one dice. Now again, this is a conditional probability, which you can try to simplify using smaller, short expressions. Suppose we want to find the probability that some event C occurs, given that D has already occurred. The probability of event C occurring, given that event D has already occurred, is given by the probability of C and D occurring divided by the probability of D occurring, right? Now, how do we translate this to the problem at hand? It basically means that what we have is that the probability of obtaining 4 on die 1 and a 4 on die 2, given that we obtained a 4 on at least one die, is equal to the probability of obtaining a 4 on die 1 and a 4 on die 2 divided by the probability of obtaining a 4 on at least one die. And the answer to each part of this fraction is supposed to already have been worked out in the question. So let's just scroll and try to find it. So this is going to give us, if we go back up, we can work out the probability of obtaining a 4 on both dice, and that would be 1 over 16. So that answer to that part is 1 over 16. So therefore, this gives us 1 over 16, and we're going to be dividing by the probability of obtaining a 4 on at least one die. And if I recall, that was 7 over 16, is it? Yes. On at least one die is 7 over 16. So we have 1 over 16 divided by 7 over 16, which of course gives us 1 over 16 times 16 over 7. These two 16s cancel, and so this gives us 1 over 7. So therefore, what this means is that the probability of obtaining a 4 on both dice, given that a 4 was obtained on at least one die, is equal to 1 over 7. That's the end of that part of the question there. Now let's move on to part C. Now part C has what looks like a box and whisker plot, which of course is vertical, but we should not be confused by a vertical whisker plot as opposed to, say, a horizontal one, right? Now, the question says the scores of a class of 30 students. So we know that there are 30 students in the class on a mathematics test were used to draw the box plot below. The total score possible is 20 marks. So the maximum score is equal to 20, all right? Now, what do they ask us now? Let's see. They tell us that, or let's analyze this diagram and see what we can actually determine from the box and whisker plot before we actually proceed to answering the questions required of us. So what pieces of information are to be shown by a box and whisker plot? A box and whisker plot is supposed to show the lowest score. It is also supposed to show the largest score. And of course, by largest and lowest, we mean the largest and lowest scores obtained, not the maximum score of 20, not necessarily, right? Is it supposed to show the maximum? All right, lowest and largest score. It is supposed to show the lower quartile, Q1, or what is referred to as the 25th percentile. It is supposed to show the upper quartile, supposed to show the upper quartile, Q3, and of course, it's supposed to show the median Q2, right? Let's see if we could actually identify those from the box and whisker plot. So clearly, the lowest score is, of course, 4, and that's where the lowest tail extends to, right? So this value right here is 4. The lowest score is 4. And clearly, this value here is 20. So the lowest score is 4, and the largest score is 20, right? Now, what about the lower quartile? The lower quartile is where the box actually stops. So if we go across, let's try to go across here and see what value that gives us. So going across from here. Now, this looks like midway between 6 and 8. And so that corresponds to 7, right? So the lower quartile is 7. Now, if you were to try to analyze the scale on these divisions, between 2 and 4, say we have 1, 2, 3, 4, 5 divisions. So between 2 and 4, we have 5 divisions. So that interval is basically 2 over 5, which is equal to 0.4. So therefore, each of these small divisions represents 0.4 marks. And so in this particular case, we have 6, 6.4, 6.8, 7.2, 7.6, 8. And the mark at the lower end of the box is between 6.8 and 7.2, exactly midway. So that has a lower quartile of 7. So this, of course, is Q1 equals 7, right? The upper quartile, Q3, the upper quartile Q3, which should be right here. We go across again horizontally and see where that touches. Let me see now. Is this right there? No, it's kind of a little difficult to see. Let me see now. Is this right at the mark or is it midway between two marks? Struggling to see it there. It appears to be midway between the two, or I could be wrong. Is it midway? Let me try to line it up with a line. Something on the screen. Right, so it is midway between two of the marks. So right here, the mark midway, right? So yes. And so that right there looks like, so it's midway between 16 and 18, and therefore we say that the upper quartile, Q3, is equal to 17. So the upper quartile is equal to 17, the lower quartile is equal to 7. Now what about the median? The median, or Q2, which would be right here, well, almost, I think I missed it a little bit, but just right, so that's our Q2. Q2 would be equal to, now once again, that looks like midway between 10 and 12, and that gives us 11, right? So we've managed to determine all of these things from our box and whisker plot. The lowest score is 4. The largest score is 20. The lower quartile, Q1, is equal to 7. The upper quartile, Q3, is equal to 17. And the median, or the 50th percentile, Q2, is actually equal to 11, right? So, looking what they want us to determine now, based on what we actually obtained from the box and whisker plot, the median score is equal to 11. That is a median score, right? Now, the range of the scores. The range of the score is, of course, is the largest minus the smallest. And so this gives us 20 minus 4, which is equal to 16, right? So that's 20 minus 4, which is equal to 16. Now, the next part of the the semi-interquartile range. By definition, the semi-interquartile range, or SIR, is equal to the interquartile range, IR, divided by 2. And of course, the interquartile range is equal to Q3 minus Q1. And therefore, the semi-interquartile range is Q3 minus Q1 divided by 2. And therefore, the semi-interquartile range is equal to 17 minus 7 divided by 2, which gives us 10 divided by 2, which is equal to 5. All right? So that there is equal to 5. Now, the next part of the question says we're supposed to comment on the distribution of the scores, and that is worth 1 mark. Now, what does this box plot tell us about the distribution of the scores? Now, if we examine the box plot carefully, we'll see that the median, or the median 11 is much closer to the lower quartile, which of course is 7, than the upper quartile, which of course is 17. So basically what this tells us is that there is a larger number of scores closer to the lower values than to the larger values. In other words, and there's a greater part of the distribution, which of course is closer to the lower scores than they are to the larger scores. And that basically what this tells us about the distribution. Again, we can use the closeness of the median to either the lower quartile or the upper quartile to give an idea of how the scores are distributed. And in this particular case, because the median is closest to, or closer to rather, closer to the lower quartile than it is to the upper quartile, then this tells us that there are a large number of scores which are closer to the lower marks or the lower ends than to the upper end. Now, the next part of the question, it says that we're supposed to state one reason why it would be impossible to determine the mean score from the box plot. Now, the box plot simply does not give us enough information to determine the mean. Now, how exactly do we calculate the mean of the scores? The mean is equal to the sum of all scores divided by the total number of scores. So in order to calculate the mean, we at least have to have those things. Now, at the start of the question, they actually gave us how many students were actually in the class, 30 students, but all they gave us in terms of the marks, well, they gave us the maximum possible mark. And from the box plot, we can only see the highest mark, and we can also see the lowest mark. And so therefore, we simply cannot determine the mean from the box plot because we simply do not have enough information, right? So we do not have enough information to determine the mean because the box plot does not give us the total scores or the total of the scores. It simply gives us the highest and the lowest score according to the data, right? So therefore, as a result, we cannot determine the mean score from the box plot, right? Now, part 5 or part 6 says, state what additional piece of information will be needed to determine the mean score. So based on this formula, the mean is equal to the sum of all scores divided by the number of scores. And at the beginning of the question, we're told that there were n equals, was it 20? No, 30 students. There were 30 students in the class, just to check, to verify. Right, so 30 students on the maths test, right? So 30 students did the maths test. And therefore, in order to actually determine the mean, we would need to find the sum of all the scores. So we would need the sum of all scores in order to determine the mean. All right. Now the last part of the question, 7, says that given that the sum of the 30 scores for the class is 354, so now they actually give it to us, but obviously part 6 preceded part 7, and obviously we could not use it, right? So given that the sum of the 30 scores for the class is 354, so let's call that sigma x. So sigma x is equal to 354. And the sum of the squares of the scores is 4,994. So we have sigma x squared is equal to 4,994. They want us to determine the standard deviation for the data set. Now, this formula is normally quoted at the front of the booklet in the list of formulas or formulae. And so therefore, this formula for the standard deviation, S is equal to, let me see now, S squared, which is a variance, is equal to sigma x squared minus sigma x all squared over n divided by n minus 1. So that right there is a formula for the variance. And of course, the variance and the standard deviation are related. The standard deviation is just a square root of the variance. So let's proceed to finding the variance. So we have s squared is equal to sigma x squared, which is 4,994 minus 354 squared over 20. This is all over 20 minus 1. So we have s squared is equal to 4,994 minus, let's go to our calculators and work that out. So 354 squared, 354 squared divided by 20. And that gives us 6265.8. Whoa. Sum of x squared is a formula here. Sum of the squares of the scores is equal to something right 354. So the formula is sum of x squared minus, all right, so let's see, right. So let's see, 354 squared divided by 30. So all right, so n is equal to 30, not 20. That explains I was getting something negative. So this should be divided by 30, and this would be 30 minus 1. Right, so let's check this again. So 354 squared divided by 30, that gives us 4177.2. So 4177.2, and this is all over 29. All right, and so s squared would be equal to, so minus 4,994. This is 816.8 divided by 29 equals 28.2, and therefore the standard deviation is equal to square root of 28.2, and so S is equal to 5.3. So standard deviation is equal to 5.3. All right. So this question involved, of course, probability and a little bit of statistics. And in this question, we're required to analyze a box and whisker plot, and of course, calculate the standard deviation of scores in a test. And this is the end of the question.